Alright, welcome back everyone. So we're kind of skipping around a bit in this module, similar to the way we did in Module 1. But this next section, 4.8, it's titled Polynomial Equations and Functions. So we're going to kind of review on those. But we're also going to look at, we're going to do a little bit of problem solving that will involve some quadratic equations. Okay. Alright, so we'll get started. So I just kind of restated some of this. But remember, a quadratic equation, guys, is literally taking a quadratic function, and setting it equal to something. And then rearranging it such that the quadratic function is equal to 0. Okay? So this is the standard form in which you can express a quadratic equation. And then remember, a, b, and c are just real numbers. Sometimes b and c can have values of 0, which means the middle term and the constant term end up disappearing. And so again, here's the standard form to express, or for a quadratic function. And then I kind of wanted to review on, because there's a couple problems in your homework, the zeros of a function, okay? And that's really what we were working on in section 7.4, finding the zeros of all of those different quadratic functions that we saw. And that just means that to find the zero of a function, you take your function, set it equal to 0, and you solve it for x, okay? Or in other words, it's the values for x such that if you were to substitute them into the function, they'll give you a value of 0. Okay? So for example, if c was a 0 and we plug that into the function, we should get a value of 0. Geometrically, if you remember, that means that that particular point associated with that 0 for x, and that value of 0 for y, or for the function, is an x-intercept. Okay? And so here we see we've got this quadratic function. I'll write it x squared plus 6x plus 8. And if you were to set it equal to 0 and solve for x, we can look at the graph until determine that we're going to arrive at values of -4 and -2, okay? Because those are the 2 points on this parabola such that their y-coordinates are 0, or in other words, those are the zeros of the function, okay? So I'll go dot, 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 and then we'd end up getting x is equal to -4 and -2. But the x-intercepts are the points -4, 0, comma, -2, 0, okay? Alright, so the term 0 refers to the x-coordinate of the x-intercept. So they're related, right? Alright, let's look at a couple examples here. It says, use the graph of f of x to find the x-intercepts of the graph and the solutions of the equation. Okay? Well, when they say solutions of the equation, they mean what would the solutions of the equation be if you take that quadratic function, set it equal to 0? Well, this is tantamount to finding the zeros, okay? Or solving this equation again. We've already discussed that in section 7.4. This one is factorable. You can factor it. We can also use the quadratic formula. But fortunately for us, guys, this function is graphed, and it pretty easily reveals what the zeros are because it crosses the x-axis right here at -5. Okay, and so one of your x-intercepts is going to be the point -5, 0. And then over here, this is not so obvious, but we could double check in Desmos, x squared minus 4x minus 45. or in our graphing calculator, y equals x squared minus 4x minus 45. Okay. And now looking at this, you can see, well, right there it crosses at -5. And then over here, that's at 9, the integer 9. Okay. Now remember, Desmos is nice because you can zoom out too. This is a very elongated parabola. Look at this one. Its center is way down here. Whenever y is -49. So, all right. So the other x-intercept, its coordinates are -9, 0. And furthermore, guys, I guess. Oh, never mind. The solutions, I'll write this, are going to be x is equal to -5 and I wrote -9. I meant to write +9. I'm sorry, -5 and +9. Remember, this is not an ordered pair. These are just the values of x that solve this equation. Or in other words, these are the zeros. The solutions of the equation, that's just another way of saying the zeros of that quadratic function. Okay. All right, let's look at example 2. Well, example 2, it's the same thing. We want to find the x-intercepts of the graph of this quadratic function, and we want to find the solutions of the equation. Now, one thing you'll notice is that the order in which the terms are listed are ascending. Okay, so the order, typically, as you guys know, we want our x squared term to come first. We want those powers of x to be descending. In fact, we refer to, when a polynomial is written that way, we refer to it as being written in descending order. Okay. All right. Well, this one is actually factorable as well, so you could solve it by factoring if you wanted. Okay. So if we were to set it equal to 0, we'd end up getting values for x of, and then we can look at the graph again, or graph it in Desmos. This is probably going to be -4, and this one over here is probably going to be +8. So -4 and 8. And those are the zeros of that function. And then the x-intercepts will be the ordered pairs -4, 0, and then the second ordered pair 8, 0. Okay. All right. Well, it looks like I may end up doing all of this in one video. Well, we'll see. Okay, now what we're going to do, guys, is we're going to do some problem solving. Okay. We've got a couple word problems right here that we can help model what's going on, using a pretty ancient theorem. You've probably heard of this one. It's called the Pythagorean theorem. All right. And so let's go over this theorem first, because we're going to need it in order to solve both of these problems. Okay, now this theorem was, I guess, the person credited with having discovered this theorem went by the name of Pythagoras in ancient Greece. Okay. And the theorem deals with how the sides, or the lengths of the sides, are all related for any right triangle. Okay, so we've seen triangles before, but what about a right triangle? What's specific to it? Well, a right triangle, guys, is just a triangle in which one of the angles is 90 degrees, as you can see here. Or in other words, a 90-degree angle is basically the corner of a square. Okay. And so this theorem applies to, it's a relationship of the lengths of all three sides to any right triangle. Okay? And it basically says this. It says that if you square the length of each of the legs, that's these two sides. The legs are the sides that make up or that form the right angle. Okay, those are what we refer to as the legs. Okay, so A and B represent the legs, and C, or your diagonal side, is known as the hypotenuse. You may have heard of that as well. Okay. Every right triangle has a hypotenuse, and every right triangle has two legs. Okay, the hypotenuse is just what spans those two legs. It's always the side that's opposite your right angle. Alright, so what does this theorem say? Well, it says that if you take the square of this leg plus the square of the other leg, add them together, that will equal the square of the hypotenuse. Okay, this is what it would be in algebraic form. A squared plus B squared is equal to C squared. Okay, arguably, probably the most famous or most well-known theorem in mathematics. Not a really profound theorem, guys. It's not actually very difficult to prove at all, but it is probably the most well-known theorem, and it's used a lot. So anyway, let's go ahead and take a look at example 3. So example 3 says a triangular cell is 9 meters taller than it is wide. And then it gives us the area of the cell to be 56 square meters, and then we are asked to find the height and the base of the cell. Okay. Well, this cell, guys, is a right triangle. If you look at the little picture here. And so we can use the Pythagorean theorem to relate the lengths of these different sides, because we're given some information about the sides, also about the area. Okay. So we can draw a picture. Remember, drawing a picture is always a good step, if applicable, in trying to solve these word problems. Alright, so I'll call this side, this could be A, this could be B, and this could be C. Okay. Now, I want you to note, though, that A is going to represent the height of the cell. Okay. And then B, fittingly enough, will represent the base. Okay. And that's what we're asked to find here. And we are told that the triangular cell is 9 meters taller than it is wide. Okay. So we can let, well, the width is also the base. So we're kind of using these terms interchangeably. So this side, the height, is 9 more than the base. Alright, now how's that going to help us? Well, we can set up an equation. We can say, well, let's go ahead and say B is equal to the base, or the width, okay. And then we can express the height or the length of this side A, okay, in terms of B, because it says that the cell is 9 meters taller than it is wide. Okay, so if it's B meters wide, then B plus 9 would represent the height. Okay. And B plus 9, actually, I'm not going to call that side A anymore. I'm going to replace it with B plus 9. Okay. Alright. So I've got my variable, or my unknown, defined here. Now, I need to come up with an equation that relates this information. Now you may think this is weird. They start talking about the area of the cell being 56 square meters. Well, that's important, guys, because that relates these two sides together to a specific. Hold on, just. My computer froze again. Yeah, so if you recall from your geometry classes, remember how the area of a square, or let's say a rectangle, okay, was width times length, or length times width, however you want to define those dimensions, length times width, okay, you just multiply the two. Well, all a triangle is basically half of a rectangle, okay? So the area of a triangle is 1/2 times the length times the width, okay? Well, we're given, or we know in a sense, the length and the width. That's just these two legs, or these two sides of this triangle, okay? So this sentence right here is going to allow us to relate this information to a value of 56 square meters. Okay, so using that formula, and I'll write this in the notes. The area of the triangle, remember that's the symbol that we use for a triangle, is equal to 1/2 times, you could write this as the base times the height if you want. It doesn't matter what we call those dimensions, okay? So the area of the triangle, well, we're given the area of the triangle. It's 56 square meters. Okay, so 56 square meters is equal to, and we know the base and the height of our triangle here, or at least we have those defined in terms of b. Okay, b is the base. And b plus 9 is the height, because it tells us that the cell is 9 meters taller than it is wide. So 1/2 times b, which is the base, times b plus 9, which is the height. Okay? And this is our equation right here. Now all we need to do is solve this equation. Actually, I'm going to take that first factor of b out of parentheses. We don't need it in parentheses. So if I were to try to solve this, first thing I might do, guys, is try to eliminate this fraction 1/2 by multiplying both sides by 2. Okay, I'll just recopy this. And I'm going to throw this unit away here. We can think about what units need to apply here in a minute. Okay. If I multiply both sides by 2, okay, 2 times 1/2 is 1, so those will cancel. Okay, you can just cross them out. And then 2 over here on the left-hand side, 2 times 56 is 112. Okay, so 112 will equal b times b plus 9. Alright, so all we've done there is just eliminate the fraction, but by doing so, that's really made this look less intimidating. Now what I need to do is distribute this b here. So b times b will give me b squared, and b times 9 will give me 9b. Okay, equals 112. And now, guys, if you notice, we have a quadratic equation. Okay, and we need to solve it for b. Now I'm going to put this quadratic equation in standard form. I'm going to move this 112 over here to the right. If I do that, its sign will become a negative. The left side will be 0. So we'll have b squared plus 9b minus 112. Okay, and to solve this one is actually factorable, so you could factor it if you want to solve it, or we can use the quadratic formula. Okay, so I'm going to say using the quadratic formula, we will get that b is equal to, and let's see, let me find the quadratic formula. Okay, here it is. So let's go back and define our coefficients. And remember, we're using b's instead of x's. Don't confuse this b with the b that's in the quadratic formula, because that just refers to the 9 here, the coefficient. So a is 1, b is 9, and c will be negative 112. Okay, so I'm going to plug those in. A is 1, b is 9, and c is negative 112. I'm going to calculate this, and we get two nice integer values for x here. We get negative 16 and positive 7. Okay, negative 16 and positive 7. Alright, well, only one of these values, guys, is going to be appropriate for our problem. B represents the base, remember? Okay, so we couldn't have a negative base. And this is very common lots of times when you're modeling something using the quadratic function, and you end up with a quadratic equation, you go to solve it, you'll end up with two zeros or two roots, but only one of them is going to make sense in the context of the problem. So only 7 makes sense. So having said that, we can come over here to the left and we can say, I'm going to go back to blue here. Or actually, I'll get this nice green. We can say that the base is 7 meters. Okay? And so if b represents the base and it's 7 meters, then the height is going to be b plus 9. Okay? So 7 plus 9 is 16. So the height of that cell is 16 meters. Okay? So those are the dimensions of the cell. And notice we didn't even work with the hypotenuse here. Okay? But we are going to in the next problem. Alright, I think we've got just enough time. I might go over the 30-minute threshold a little bit solving this second one. But this example 4 and the last example in this section, guys, is a pretty common problem in this class. You're going to see it again, I believe, both on the test and I think even on the final. Okay. Alright, so let's read it. The foot of an extension ladder is 5 feet from a wall. And then it starts talking about the height that the ladder reaches on the wall and the length of the ladder being consecutive integers. And then the question is, how long is the ladder? Okay. Alright, so what we'll do here is draw another picture. So I will call this side the wall. And then this will be the ground or the floor. And then we'll say that our ladder is right here. Okay. So the ladder is actually making up the hypotenuse of a right triangle, if you notice that. Okay, so the wall is one of the sides to my right triangle here. And then this distance here on the ground or the floor, that is my other side. Okay. Now we can just put, I don't know, ground, I guess. Okay. Ground or floor, something like that. Well, we know that using the Pythagorean theorem, we can relate all these lengths here. Okay. If we square the length of the wall, add it to this length, and that should equal the square of however long the ladder is. All right, so we don't know any of those things specifically. It just tells us that the foot of an extent, or well, actually we do. The foot of an extension ladder is 5 feet from a wall. Okay, so we know this side is 5 feet, but we don't know the other two. I'll go ahead and label this 5 feet. But then it goes on and tells us something about how the wall and the ladder are related. The height that the ladder reaches on the wall, so this side right here, and the length of the ladder are consecutive integers. So what does that mean? Well, that means two integers, one right after the other. Okay. So like if the wall were 9 feet, then the ladder would be 10 feet. Now the reason I know the ladder is longer, will always be the longer side, because the hypotenuse of any right triangle is always the longest side. And it makes sense because it's spanning that distance. Okay? These individual legs can't be longer than the hypotenuse. Alright, so I need to define my variable. So I'm going to use x. Well, there's two things I don't know. I don't know the wall or the ladder. Well, to me, it's easier if I let x be the smaller of those two values. So the wall, or the length of the wall, is going to be smaller than the length of the ladder. So I'll let x represent the length of the wall. And so x plus 1 will be the length of the ladder. And you may be wondering, well, where did that x plus 1 come from? Well, because the problem told me that those two distances are consecutive integers. So if x is the wall, or the smaller distance, then x plus 1, or that next consecutive integer, must be the length of the ladder. Okay? This is always the case. Anytime you're working with a word problem that talks about consecutive numbers or whatever, okay, you'll always let x be the smaller one, and then x plus 1 will be the bigger one. Sometimes you might even be working with 3, so then x plus 2 would be the third one. Okay? But anyway, now we need to come up, we've defined our variables, so now we need to come up with an equation that relates all this information. Well, the equation is that Pythagorean theorem. It tells us that if the one leg squared plus the other leg squared should equal the hypotenuse squared. Okay. All right, well, my legs are going to be 5 feet and whatever this distance of the wall is, which we're using x to represent. Okay. So 5 squared, I'm just going to ignore the units for a minute, plus x squared should equal the length of the hypotenuse, which in this case is the length of the ladder, so x plus 1. So x plus 1 squared. Okay. And now we've got our equation here. So now we need to solve it. Okay. But to solve this one, guys, the first thing we need to do is we need to actually square this binomial, this x plus 1. So we're not just squaring x and we're not just squaring 1, we're squaring everything here. So if you remember, I'm going to come down here on the left. What it means to square a binomial, it means you multiply that binomial by itself. And you have to do that using the FOIL method. So you'll say x times x is x squared. X times 1 is 1x, or just x. And then distribute the 1. 1 times x will give us another x. And then 1 times 1 will give us 1. Okay? Now we can combine those two middle x terms. So we'll get x squared plus, that'll be 2x plus 1. That's what we're going to have on the right-hand side. So I'll recopy my equation. You know, I'll go ahead and square the 5, that'd be 25, plus x squared is equal to, and recopy that trinomial that I came up with. Okay. Alright, Now looking at this, you see an x squared term in there. So you may be saying, oh, well, this is a quadratic equation again. Okay. And so if it is a quadratic equation, we need to get it in standard form. We need to try to solve it by either factoring or using the quadratic formula. So in other words, I need to move everything to one side. Well, if I were to do that, I have fewer terms on the left-hand side, so I would want to choose to move these two terms over to the right. And you can do that by subtracting them because they're both positive. Whoops. You can do it in one step as well. Okay. Just when you subtract them from the right-hand side, make sure you put the x squared term with the other x squared term and the constant with your other constant over here. Okay, so on the left, these all cancel out, leaving us with nothing, or in other words, 0. And then this will equal. An interesting thing occurs on the right-hand side. X squared times x squared is 0. So guys, you end up losing your x squared term. You'll have 2x left, and then 1 minus 25 right here is negative 24. Okay? So this turns out to actually not be a quadratic equation because there's no x squared in there anymore. Okay? When we went to put it in standard form, it ends up just being, it's like setting a linear function equal to 0. Well, we can solve this one easily enough. We'll add 24 to both sides. So we'll end up with 24 on the left-hand side is equal to 2x. And then we'll divide both sides by 2. And we'll arrive at x is equal to 12. And this is going to be feet. Okay? 12 feet. Well, you got to go back and look at what your problem is asking. It's 12 is x, and x represents the height of the wall, or that the ladder reaches on the wall. Okay, but that's not what the problem is asking. The problem is asking for the length of the ladder. Okay. Well, if the wall is 12, then the ladder must be 12 plus 1, which is 13. Okay, so 12 feet plus 1, technically that's 1 foot, equals 13 feet. Okay, so the ladder is 13 feet long. So be careful on this, guys, when you just pay attention to what the question's asking for. You'll come up with a value for your variable, but that variable may not represent what the question's asking for. You may have to go back here and substitute to find that other unknown value. Okay. But anyway, like I said, you're going to see these problems, or this specific one problem, 2 or 3 more times throughout this course. Okay. All right. Well, we finished up in just a little over 30 minutes, the entire section. Okay. All right, guys. So, what we're going to jump back to chapter 7, and we're going to cover section 7.5. And that will be on basically analyzing quadratic functions or their graphs. Okay, so I'll see you there.